Dmitry, and I'm a part of Exactpro team. If you're watching this, we assume that you're interested in software testing. This series is in no way a comprehensive review of the ISTQB Foundation Level syllabus, but we hope it will provide you with a good idea of what this certification program is about. We have tried breaking it down for you to help you overcome your fears and successfully pass the exam. If you're new to our channel, don't forget to subscribe and remember to hit the bell button to see the new videos coming soon. Most people these days have had an experience with software that did not work as expected. A delay while waiting for a credit card to process or a website not loading correctly are common examples of that. Some errors can be quite trivial, but others costly and damaging, and may even result in injury or death. The terms like errors, defects, and failures are usually synonymous in our everyday speech. But when it comes to software testing, it is necessary to distinguish between those three. Let's review them as a chain of events. A person can make an error, which can lead to an introduction of a defect, also known as a bug, in the software code. If that defect is executed, it may cause a failure of the system. For example, you get distracted and make a mistake while coding. That's an error. As a result of that, your code calls for a monthly report instead of a daily report. That's a defect. So, when the script is executed, it calls for a monthly report, which was not what the specification required. That's a failure. The saying goes, to err is human, to forgive divine. Unfortunately, there is no divine component in software testing. It is quite unforgiving. Here is an example of a software error with catastrophic consequences, the so-called 2010 flash crash. It happened on the 6th of May 2010, lasted for about 36 minutes, and during the collapse stage caused a loss of $1 trillion for the US stock market. This event was caused by a number of factors. One of them was a faulty sell algorithm that disregarded the prices while only taking the volume information into account. Considering the speed at which the modern exchanges work today, it only took minutes for this buy-sell cycle to hurt the world's economy. One of the most important questions we need to ask ourselves about software defects is when do they arise? This picture displays 4 possible scenarios. In the first case, everything was done at every stage of the life cycle. This is the best case scenario, but not a very realistic one. Besides, it contradicts the testing principles we are going to go over later in this video. The absence of bugs is deceptive, and if you don't see them, it doesn't mean that the software is defect-free. In the second case, the requirements and the design stages went well, but some bugs were introduced during the development stage. These bugs need to be discovered through testing and then get resolved. This is a more lifelike scenario which testers encounter on a daily basis. The third scenario, the mistakes are made during the design stage. If they are not found and closed, the product will have design flaws, still correctable, but at a higher cost. And finally, the worst case scenario, the mistakes are made during the requirement stage and reproduced from there on, snowballing until the product is released. As a rule, such mistakes are the most expensive ones. Exactpro's QA specialists have been observing such scenarios on numerous projects with various clients. Okay, it might seem a bit illogical that software defects even occur in the code. After all, every party involved loves quality and hates bugs, yet they still arise. Why? The reasons are too many to mention. One of the biggest causes of that is failure to communicate, the lack of clarity between different project stakeholders. Botched or misrepresented requirements and cognitive biases can introduce mistakes which can lead to defects which end up causing failures. Time constraints are another crucial factor. Project scheduling is often done on incorrect assumptions. Impending deadlines bring pressure, loss of concentration, and mistakes. Automation or the lack of thereof is another contributor. Sometimes we don't have enough resources to successfully implement it in order to achieve the required coverage. Or it can be the other way around. Instead of running a manual test that only takes 5 minutes, we spend 5 hours automating it and still make a mistake. The list goes on. The last one worth mentioning is lackluster third-party tools. What makes Exactpro stand out is build software to test software policy. We make our own tools and adapt them to the needs of our clients. So rigorous testing is necessary to discover the bugs and increase the quality of the system. This is measured in terms of the number of defects found, the amount of tests run, and the degree to which the system is covered by tests. We can do this for both the functional attributes, for example, sending and receiving an order correctly, or for the non-functional ones, for example, sending and receiving an order quickly. In other words, the quality is the degree to which the system satisfies the stated and the implied needs of its various users. The mindset we want to adapt while testing is different from the one we use in development. If a goal is to create something, we tend to work positively and constructively to solve the problems and to deliver the product that meets a specific need. However, when we test this product, we look for its flaws. Our attitude is critical and destructive. In this case, our goal is to prove that the product is short of expectations. Carl Sagan stated in his Rules of Skeptical Thinking that we should not cling to the hypothesis just because it's ours, and we should always get an independent confirmation. This is the common practice of a scientific community. Suppose you're the head of the movie production team. You pick your actors and locations, you work on a storyline, and you frame each shot carefully. You spend weeks pacing the cutting room floor. You add the soundtrack. The release date is here. The movie is ready, but all of this doesn't mean that you made a good one. For every Dark Knight, there is Batman and Robin, and for every Star Wars, there is Battlefield Earth. The critics and the viewers have a different mentality than the production team, and they're not going to overlook the plot holes, the poor acting, and the bad taste. The same goes for software testing. Building software and testing software differ in the underlying logic. We do not mean that a programmer cannot be a tester, and a tester cannot be a programmer, although these are often separate roles. Sometimes a good movie director will be as objective about his own work as the critics. There are countless stories about movies going through extensive reshoots just to get some of the finer points right. Steven Spielberg revised some of his approaches while filming his classics like Jaws and E.T., and maybe that's why his movies still stand the test of time. So with the right mindset, programmers can test their own code, and they can resolve many issues before anyone else sees a prototype. Business analysis and marketing staff should review their own requirements. System architects should look over their own designs. However, we all know it is difficult to find your own mistakes, so all of them often rely on others to help test their work. This other person can be a fellow analyst, designer, or developer. Or you can involve a quality assurance expert. In fact, testing may involve a chain of people, each carrying out a different level of testing. We can identify several degrees of separation between a person who wrote the code and the one who checks it. We organize them in a simplified progression. So, tests can be run by a person who wrote the item under test, another person within the same team, such as another programmer, a person from a different division of the same company, and finally, tests can be designed by a person from a different organization, such as specialized technology vendor. Early in the lifecycle, requirement reviews by someone other than the author help find defects before coding starts and help build the right software. After the coding is complete, the software can be tested by an external team. This separation avoids author bias and is often more effective at finding defects and failures. We should note that independence is not necessarily the most important factor in high-quality testing. Developers can be self-critical and benefit from knowing their work. Some software development methodologies insist on developers designing tests before they start coding and executing those tests continuously as they progress. This approach encourages early testing, which is cost-effective. This practice is one of the key testing principles promoted by the ISTQB Foundation Level syllabus. Let's take a look at all of them. Principle 1. Testing can show that defects are present, but cannot prove their absence. Testing reduces the amount of undiscovered defects remaining in the software, but even if no defects are found, it doesn't prove that the system is perfect. The absence of proof is not the proof of absence. The fact that you gaze into the night sky and see no exoplanets doesn't mean that they are not there. We have been looking for Earth-like planets for a very long time, but it wasn't until 1995 that we found one. The same goes for the search of Planet 9 of our solar system. We haven't found it yet, but it doesn't mean that it's not out there. Testing is aimed at proving that software contains defects, rather than proving that it doesn't. Confirming that it doesn't isn't possible anyway. Principle 2. Exhaustive testing is impossible. Testing all combinations of inputs is not feasible except for the trivial cases. Instead of exhaustive testing, it is recommended to focus the efforts on risks and priorities. Even with the simplest program that requires entering a number into a field, amount of all possible test case combinations can become infinite. Now imagine we're testing a complex exchange platform. Add the limitations applied by time and budget, and you will see why the best practices suggest that we target the most important test cases. Principle 3. Early testing. Testing activities should start as early as possible in the software development lifecycle and should be concentrated on predefined objectives. The reason for that is very simple, and we cannot stress its importance enough. The earlier we find a defect, the cheaper it is to fix it. Besides, a defect discovered at the requirement stage is much easier to fix than the one found during the acceptance testing, where each component can affect the other ones in an unpredictable way. As you go from stage to stage, the cost of fixing a bug grows exponentially. Principle 4. Defect clustering. A small number of modules contain most of the defects found. According to the 80-20 Pareto principle, 80% of defects are usually found in 20% of the source code. The explanation for this effect can lie in the fact that some parts of the system are more complex than the others, or written according to a lower quality specification. What it means to a tester is that if a bug is found in a certain part of the system, the chances are there will be more of them hiding nearby. Principle 5. Pesticide paradox. If the same tests are repeated over and over again, then sooner or later they will no longer find any new bugs. Let's just say the bugs that survive the most intensive testing routine become in some way immune to this test set. It is similar to bacteria becoming resistant to a certain type of antibiotics if they're used repeatedly. Testing an order with the same parameters might be successful at first, but repeating it over and over again will soon stop bringing any results and give us a false sense of the absence of defects. But try changing one parameter and we'll probably uncover new bugs. To overcome the pesticide paradox, test cases need to be regularly revised and the new ones need to be written. Principle 6. Testing depends on the context. Testing is diverse and context dependent. For example, safety-critical software is tested differently from an e-commerce site. Take Google, for example. They can afford to release an under-tested product and let the users do their work for them. But what could be acceptable for Google is hardly applicable for software powering medical equipment or spaceships. This is a completely different level of accountability. The stock exchange software lies somewhere in between. It will not kill anyone if not tested thoroughly enough, but it can hurt investments, jobs, and economic stability. Principle 7. Absence of errors is deceptive. Finding and fixing defects doesn't help if the system we've built isn't usable and does not fulfill the needs and expectations. If the system doesn't do what the user wants from it, the absence of bugs is pointless. During the last segment of this video, we're going to review the fundamental test process. It consists of the following 5 steps. Step 1. Planning and control. This is what we usually have to do to create a test plan. We determine the risks. We need to know what the dangers are. And we identify the objectives. We have to understand why we're testing, what we're testing. Next, we need to determine the test approach. We have to understand the test requirements and details of how to perform it within the organization, as well as which testware we're going to use. Then we determine the resources. We make sure that the human and hardware resources are well defined. And last, we determine the exit criteria. We need to understand when to stop testing. Step 2. Test analysis and design. Test knowledge used for test analysis and design is called the test basis. We study it to create our tests for the most critical software aspects. And, by the way, these have to be represented in a testable way. There is no place for ambiguity. You can't just say that software has to cope with a large amount of data. A large amount can mean different things for different people. A more testable requirement would be that the system has to support 250 million orders a day. Another thing we have to make sure is that our system matches the operational environment used by our clients. And test analysis answers the question of what to test, while test design answers the question of how to test. Step 3. Test implementation and execution. Here we take a component of a system, apply prepared sets of inputs and compare them to the expected results using our tools in a simulated setting. If a test fails, we start the process of finding, analyzing, and removing the cause of a failure in a system, also known as debugging. We test the corrected software again to ensure that the defect was indeed fixed. This is also known as confirmation testing or retesting. We also have to make sure that the correction did not introduce defects in the unchanged areas of the software, and that the fixed defect did not uncover or cause other bugs. This is called regression testing. Step 4. Evaluating exit criteria and reporting. Evaluating exit criteria is an activity during which test execution is assessed against the defined objectives. This is where we confirm that we have done enough testing. Step 5. test closure activities. During test closure activities, we collect the data from the completed tests and analyze the facts and numbers. We also finalize and archive our tools for later reuse. This concludes our today's video. In the next one, we're going to go over chapter number 2 of the ISTQB Foundation Level syllabus, titled Testing Throughout the Software Lifecycle. If you're new to our channel, don't forget to subscribe and remember to hit the bell button to see the new videos. My name is Dmitry. Goodbye.